I'm Jordan. I'm the CTO, co-founder of Astria. We're building a shared sequencer network, which just like, well, not just like, but similar to what Espresso has been showing off lately, and gonna walk us through here what we have and what that means. And really what we're trying to show is, we talk about this thing that deploying a rollup should be as easy as deploying a smart contract. And so a big part of what we're demoing here today is how you can use a shared sequencer and how this can be possible. There will be a part here that, in theory, you could walk along on your computer, but as I get to in just a bit, you'll see it probably not practical given Wi-Fi restraints. But so when we talk about a shared sequencer, this was pulled directly from our Josh's talk earlier about what a shared sequencer is. And so the first thing we want to do is we want to get this shared sequencer, and we want to get a singular rollup running on top of it, because without anything, you're not sequencing anything. And so the question becomes, like, what does the architecture look like? This is a nice, pretty diagram, but we're going to go a little bit more technical here. It's like, what are we actually doing underneath the hood in order to make this possible? And so this is more of an internal architecture diagram of what we're going to be running. We have shared sequencer, where the sequencer here is a Comet BFT / Tendermint, depending on your preferred terminology, based chain. And then we have a relayer which runs and it participates in a gossip network, and it also takes the transactions and writes them to the data availability. So our sequencer here is running on approximately 1 second block times, where Celestia is running at 15-second block times. At each 1 second block time, there's a gossip that's created of that block, which our conductor piece over here can read as a soft commitment to execute inside of the chain. Additionally, at the end of every Celestia block, we submit the data for all blocks that have occurred since the last write to the DA, which what we call the conductor as well can read off of that DA. What the job of our conductor here is it's the drive of a rollup. So similar to what the beacon chain is, or the engine API for Ethereum, or what OP node functions in the OP stack, this is going to be executing via a API we have here that's pretty simple to drive the deterministic execution of blocks. It does this in such a way that is blockchain agnostic. It doesn't actually know what Ethereum blocks are. It just knows that it receives a hash back in return. And we have a modified Geth node which consumes that API and is able to send those through to our shared sequencer. And in the end, you as a user, get a completely processed transaction. There's a little bit of tooling here that I'm going to use to spin this up locally and show you like how all it works. We have a whole bunch of DevOps tools. So if you were to do this on your own machine, you would need Docker and Kubernetes tooling, and we use Helm and then some commands here to make our scripting easier. And then if you were also following along, these are the 2 GitHub repos I'm going to be interacting with. We have others, but these are the 2 for kind of demonstration purposes. Our dev cluster repo has all of the configuration and whatnot. We also have like a mono repo for most of our Rust-based code. And then those are going to spin up a whole bunch of Docker images. I put this list here because this is why if you were to grab your computer and go to run things, it would need to pull all of these images. And the Wi-Fi is always great at conferences, and I think that even just having 12 people in this room pulling a list of, eyeballing at 15-ish Docker images might be a bit painful. I've already pulled all of these locally, so I'll be able to walk through kind of how we spin up this whole system, as well as how we interact with it, and then we can go through and kind of demonstrate what's happening behind the scenes. All right, that said, let's actually deploy this thing. So I'm going to go over here into, let's clear this. So within the dev cluster repo I referenced earlier, we have a whole set of Kubernetes configuration pieces to deploy things. Thankfully, you don't actually have to know how to use Kubernetes in order to get deployed, because that would be a terrible experience for someone trying to test this. The first step to create this would be to create a cluster. I'm not going to actually run this command right now because I have already spun up my Kubernetes instance because this starts all of the image pulling. And then once we get this done, this is all in the README of our repo as well in terms of what it takes to basically get things spun up. The first thing we're going to do is we're going to deploy Astria local. Cool. This is going to spin up a couple of Docker containers, which I can, and containers in Kubernetes, which we can see here. Yeah, there's going to be some. The magic of Kubernetes is that these things will reboot until they come up. So within our sequencer, yeah. Yeah, let me see what I can do to. Yeah. Is that a little bit better? Here, let me make it even bigger here. There we go. Okay, so now what we've spun up when we do this, we have two things. We have a Celestia local network, and then our sequencer just came up online. So if we go back and reference our slides here, I've spun up this data availability, which we have a Celestia local network, as well as the sequencer and the relayer. These all exist in one. Let's just leave that up. And slide over. So in our sequencer here, we can see that we have a Comet BFT-based chain. We have the sequencer, and then we have the relayer that I alluded to. If we look into Comet BFT here, we will see that we are producing blocks rather quickly. There's nothing going on in these, though. We don't have any chains added to it, right? And if we look in our sequencer, we'll see there's nothing happening because there's no transactions going through. This is the app side of our chain. We are built on top of, instead of a Cosmos-based chain on top of Tendermint, we have a Rust app that is built on top of the ABCI interface. And then the relayer here, you can see submits blocks to the data availability layer, handles the sequencer blocks, and every so many blocks, it will write to DA when there's another DA block. There was another one. Great. Let me zoom in on this one too. So, cool. All right. So we have that deployed. Now we want to deploy a rollup. Well, let's do this the simple way. We should just deploy rollup. And we're going to deploy a whole bunch of stuff now. We can go back over here, and we can see we have spinning up. We have three different things. We have this Geth container, which contains what I called the conductor, again, the drive of our rollup, as well as an instance of Geth. And then we also have a block explorer, as well as a faucet. So if we go over to our browser here, by default, it deploys a chain at this address. We can see in MetaMask that I'm connected to the wrong network. Let's connect to LocalNet. Yeah, we have 300 tokens in this. By default, this account is funded. See 300 and nothing. We can go here. We can go to our faucet. And let's send some funds here. This will come from our other account that I have linked here. We're just going to send through, request, and then it should show up here, but MetaMask is sometimes buggy. If we go over here, we can do a cast balance, and we can see that we have transferred money pretty quickly there. Additionally, like we just did a very simple account transfer, right? If we look at, let's see if I do a cast balance. Okay, this other account, you can see that it used to have paid some gas and paid for some tokens. Additionally, like I mentioned before, we have a block explorer, so we can just go to we have Block Scout configured to load on this. We can instantly load, see our transaction here in Block Scout. And that's all fine and dandy. Additionally, we have some test scripts here. We have this like EVM test data script that we created, so we can just let's say it's create. I'm trying to remember what my command is for test data. Generate transactions. Yeah, so we can generate some transactions here. This will start running through. Foundry script will run through. We're going to do, like 30 transactions. Runs it usually about one every 6 seconds or so here. It's going to go through. We can go look at our block scout instance here. And we can again see live these transactions showing up, creating some token minting, creating contracts, just populating us with some test data here. This is all fine and dandy. We have a Geth-based rollup that functions generally like Geth, but we promised you a shared sequencer. We go forward to, we go here, it's like, oh, there's one, but what we actually wanted was this, right? We wanted to see that we have 2 sets of RPCs and 2 rollups here that are running. So why don't we go back here, and while we have all these transactions executing, we can go here and we can say, oh, I want to create a new rollup. So let's deploy a rollup, and we need to pass it 2 things. One is a name. Anyone want to give me a random name just to show that I didn't pre-program this? GM. All right. And then, anyone got a favorite number? I have to, 7? I'm going to do, how about 7 sevens? We'll do some 7s there. Cool. So this is going to be our roll-up name and our network ID. These will be distinct, and we'll be able to send transactions to both of them and see that they go through without impacting the other. So if we go back here to our Kubernetes setup, we can see we have 2 distinct things that are deployed here. We have 2 different rollups. The faucet will come up as good. There we go. So we have a whole nother instance of Block Scout, a faucet, and this, GM. And we'll be able to access that now. If we go here, we had that cast. Check the balance. This is going to be at so one of our accounts has 0 there, and our other account has our same initial balance as we had before. We have transactions running over here. Let's go ahead and do the same thing here as well. We're going to just generate transactions on GM. I think it was 5 sevens. Cool. So now we have transactions going through on both of these chains. We just about finished here. If we look at this initial one, we'll see we freeze at 32. I can go here. Let's see our instance here, populating. So we've truly, we said, as easy as deploying a smart contract. It was one call. We deployed a rollup. We have transactions going through. If we go and we look into our logs of our Geth node, we will see transactions coming through here. We can see in our conductor that we're getting blocks both. Let's stop this from going through. We can see that we have 2 things going on. One is that there are blocks being received from the P2P network, as well as we have these finalized block calls, which are being made as soon as we see the data in DA. So things are being executed as soon as they come through, but they are also being finalized as soon as they're visible in the DA layer. And if we look in our single sequencer here, let's see if we can see what's going on here. Transactions going through. We can see we have quite a few blocks. We're limited in our transaction throughput at this point by the speed at which Foundry is actually sending them, not by the speed of the blocks that are actually coming in. I can. Yeah, let's see if we can get that. Yeah, I have two screens here, so we can, this will go and execute again on our default rollup. So we can see them coming through on this rollup. They're still going through here. We can easily monitor.
I guess on the sequencing side, is there
Well, there was a log. I don't know if it's showing up right now. Let's see if we set this up to auto scroll, if we can see. As one in one namespace. So we have the list of like how many namespaces are contained. I think one of these commands may have finished. So we're only processing on. Yeah. So that was kind of the demo. I realized I went through it pretty quickly here, but does anyone have any questions about kind of what's going on in the stack? Anything I can answer? Yeah, I think the reality of like this is a demo is that it's kind of early to say. In terms of latency here, it's going to be network effects, right? It's going to come down to how well connected and how close you are to everything. If you're if you are running a sequencing node and you're running a rollup node, like you can theoretically like have network latency decreased. So there's an arrow missing on here as well, which is that currently in our current architecture, this relayer has a gossip net that it starts up via libp2p that the conductor is also connected to drive. So it gets soft commitments from the relayer as well as reading firm commitments.
Oh, okay. So that's soft commitments. So you don't want the DA to be.
No.
And generally, how rollups work, right? Like where most of our, like when we use that like rollup architecture, the finality definition is usually defined on what we put like DE and rollup box. So the rollup node itself will receive input from various sources. In this case, right, like the DA layer is one source and the shared sequencer is another source, and it will choose to define what it considers finality. So like in like Geth, usually you have a head, a safe, and a final, or like 2 stages. Head in our case, and say like Optimus' case with centralized sequencer is like the moment that sequencer like connects to it, right? That would be head. Safe would be when like for their case like Ethereum gives it, and Astria would be DA, and then final would be when you pass it a fraud proof window. It could also be when you pass it a DK. Right. So there's these stages of finality, but you get your first head block, and then kind of you progress the chain. The moment the shared sequencer gets, which is again that bounded by how fast we run head.
Mm.
So in essence, the user is sending transaction, understand, to the rollup. Yep. The rollup passes it to the shared sequencer. But the rollup sends in soft finality already, if I understand correctly. The rollup gets soft finality because so the again the missing arrow is the user sends a transaction to Geth here, right? Yeah. So the user sends a transaction to the rollup RPC, which is the Geth node. That sends it to the shared sequencer. Right. And then the top thing that soft commit, the shared sequencer actually sending the block it created back to, in this case it's the user.
Okay,
We get the soft commit, but it actually sending that block back to the rollup RPC, which then executes that. And then
So it's like
Yeah. Yeah, so what's happening like in our actual Geth node here is, we alluded to like the fork choice rule, and this is to an extent, this is up to a rollup developer. The way we've done it in this is that every time a soft commitment comes in, you get a new head and safe block because the sequencer gives you a strong commitment to ordering, but it doesn't give you a firm commitment that everyone has been able to see it. Once it's seen in the DA, we update it as final.
you see, yeah, okay, but you see a bottleneck in the shared sequencer, assuming you will have a lot of rollups. Like, how does it scale? Like, so there's like roughly the shared sequencer's bottleneck is like in like a simplistic view, right? It is like whatever the ratio of block time of the shared sequencer is to block time of the DA layer. The DA layer is going to have some bandwidth limitation, right? Like so on like the limitation of like throughput of like rollups today on ETH is like ETH can only support so much call data. How much of that call data are you buying as like a rollup? So if we say 15-second block time, for simplicity, we say 1-second block time of shared sequencer, your bandwidth of transactions is 1/115th of the throughput of the DA layer, in this case Celestia. But the nicety is that there's no chance that execution is a bounding function in this because the sequencer is not doing execution. So
Yeah.
and ordering is like a computationally cheap thing at this scale, right? Like, if it's just finding and ordering. So we're not going into like a PBS thing, which is long-term how we think this will be like ordered, right? And to some degree that's like computationally maybe like more expensive. Like doing an abstract problem of calculating an optimal block is like a computationally expensive thing. So sophisticated actors do it. We just find a block time. It runs at 1.5 seconds, and there will be congestion if you say, okay, we'll say we have
Yeah. What I
pretty high, right? Like from like if we're at like 1 megabyte blocks in the shared sequencer, like every second and a half, right? Like that's a lot of
one of the things I was gonna show here in terms of showing that like we're not actually executing is that like the chain ID, which is what we call like what you could each person similar to a namespace on Celestia, you just pick some set of bytes and you post your data to that. It's just an array of it's a vector of U8s, and then the same thing with the data. Like this whole set is just a whole bunch of bytes that we never process or do anything with. It's just bytes. Yeah. Let's go to that one. Right. So we're actually working on a new component to throw in here that's like just not quite ready, which would basically, as long as you are running, because like this process of like throwing the transaction in here is fundamentally, I'd argue, like kind of flawed. Which is that like now we have to have like a direct submission. What we're working on is this piece that will kind of capture and encapsulate what we call the like MEV piece, which is the way a MEV searcher today works is that it reads over some RPC mempools and then does some stuff and then can work with builders to build the blocks. So what we'll be doing is if you have something with an ETH RPC, you can connect this to it. It'll be able to read your transactions directly out of it instead of being submitted, and then process those and submit them itself down to the shared sequencer. So you don't actually have to have your rollup have any sort of special submission logic.
going back to the throughput question, I just like ran like back of the envelope math using like the columns thing. So if the argument is that you can get like a roll up compressed to like 12 bytes, but like there's some like subtle details there. But if you have an uncompressed ETH transaction, and I'm assuming this is like a simple transfer, it's about 112 bytes. Or it is 112 bytes for like a simple transfer. So if we assume we have 1 megabyte blocks, we're looking at 99,362 transactions per block or whatever. If you use all just like ETH roll up. where you try to send a bridge transaction between two 10-way common BFT chains. There are relayers that do this, but no one pays the relay. Not yet, because there's many designs, but they all have many implications, right?
Do you have another question?
If the DA layer is very, very cheap, right, then maybe it's fine if someone just says, hey, to get like adoption, I'm just gonna like allocate like $50,000, and that is just a fund that posts data to the DA layer. Broad design space of like how you choose to. For this demo though, like it is posting the data to like the DA layer.
Yeah.
There's like a relayer component that automatically is posting.
Yeah. But so like in this design, you're basically limiting your own data throughput by that of the DA layer.
Yeah, and from like a strictly, I guess, like semantic definition of a rollup, right? When we use the term rollup, it assumes the data is posted to a DA layer, where a DA layer is itself a decentralized network. Whereas you would use the term like a Validium, right? If it's posting the data to like a data availability committee, which is generally just like someone running an S3 bucket or whatever, right? Just like off-chain data, which is presumably just like on the cloud.
Right. I mean, like some rollups. I mean, the rollups are like getting data through this process between the shared sequencer and your system too. Right?
Yeah, exactly, right?
The-
So like if they're fine with that.
There,
Yeah, and the argument for like Celestia, right? Is like why would you post it on Celestia? Like it always the like data availability sampling, right? It's the question of like the security that a rollup wants to give. Theoretically, we assume, right, that rollups want to be able to run light clients that can then receive fraud proofs or like ZK proofs, right? But they have the guarantee that the data of that proof is easily like findable or retrievable. And again, the benefit of like Celestia, right, through data availability sampling, is that you can have a very large amount of data, right? Say these 128 megabyte blocks on like a 30-second window, like a 15-second window, right? But you can prove that like a given proof was for data that was present in that without having to store all of the data, because you now have a relatively high bandwidth system, right? And we're looking at like, call it like 256 megabytes a minute, right? That's not that much bandwidth, but it's not nothing.
So like in this, the censorship thing you mentioned, like is there also another scenario, like if the DA layer is already like at capacity and your sequencer can't afford for whatever reason to get its data in fast enough, like how do you catch up in that scenario?
Yeah, again, it's a fundamental question of like, what is the ratio of bandwidth the sequencer needs relative to the DA layer, right? Like, if it's a tight integration, right, where the shared sequencer must post all that DA layer, to some degree the shared sequencer has to be throttled to the capacity of the DA layer, and again, you have these censorship attacks, right? Same thing exists on like rollups on Ethereum today, right? Like, someone could just say, right, there could be a cartel like validator that say, like, yeah, we know who the signer for the sequencer or the relay or whatever of Optimism Arbitrum, and we're just going to censor them just to like mess with them, right? They usually have the ratio of kind of throughput is such that like they batch relatively infrequently, so they have a relatively like low ratio of like needing to buy a relevant fraction of all data on the L1, right? They batch every like 30 seconds or whatever, or every minute or whatever. But again, it's all that ratio. But yeah, if we run into something where like the throughput of all the rollups on the shared sequencer is like starting to like surpass the capacity of the DA layer, you get in this kind of awkward question of like, what if you fall behind? How can you catch up, right?
Yeah.
There's just like a structural question, and like how you handle that is like generally you would assume that you would take a relatively conservative position on like the throughput the shared sequencer will like guarantee relative to like the overall throughput of like the DA layer.
I mean, to me, like it just makes more sense to like let rollups themselves figure it out, and like if they value, faster finality through the DA layer, they'll pay it more rather than trying to force everyone.
It's a little bit of like my assumption, right? But a lot of this is also like the large premise, right? Is like we use like the term, right? Like we believe like